we are now going to talk through a few counterintuitive situations that, again, still we're trying to apply Newton's first and second law, everything we know about our central force model, but now these are things that might not make a lot of sense. So the first one is a situation where you're spinning a cup of water in a vertical circle, and that's what this picture shows. This cup here is open on top and actually has water inside, and it is going in a vertical circle. So this nun, she's spinning it in a vertical circle and is not getting wet. She's smiling because the water is not falling out. So okay, I guess I've answered my own question. Can you spin a cup of water in a vertical circle so that the water doesn't fall out? Well, I don't know if you can. There is not quite a trick to it, but there's something you need to think about. So since I've said that the answer is yes, you can see her doing it, what now? Can you explain why? Why does this work? Why does the water not fall out? And this is important, that if this puzzles you, you haven't really mastered Newton's second law and circular motion. So we're going to go through some situations that are really related to this and that are hopefully a little easier to analyze, but the same analysis that we do for a roller coaster still applies in this situation, which you should come back and think about more. Instead of analyzing the cup of water, which is a little confusing because there's a liquid in it, we're instead going to analyze a roller coaster. And in particular here, we're going to talk about a roller coaster going through a loop. So in this situation, it's the question of why doesn't the roller coaster just fall off the loop? Now, your thought might be, oh, no, there's a bunch of safety, so it can't. Well, the people don't fall out. And if you've been in a roller coaster that actually does this, there's just a lap bar. In many of these, you're not strapped in incredibly well. It feels like if you wanted to, you could jump out, but yet at the top of the loop, you don't fall out. Now, it's been a long time since I've ridden a roller coaster, but I'd be willing to get on one and go through a loop-de-loop like this because I believe in physics. So let's try to think about what's going on. So we're going to analyze this roller coaster loop. We're going to right now only be looking at the point at the top and the point at the bottom. Analyzing everything that's in between can get a little complicated, but we can do these 2 points. So the first thing to think about is that it's faster on the bottom, right? So it's going through our loop this way, and we could imagine that this is either initial or final, and that this is in between. It's faster at the bottom than it is at the top. Now, one way to know this is to just think about as it starts going up, it slows down, right? Because gravity is opposing it. In this case, it's like a ramp, and in this case, it's also like a ramp. So gravity is slowing it down. A second way of doing this analysis, which we'll start on the following week, is actually using energy. So energy is even a better way to relate what's happening at the top or the bottom, but for right now, all we need to say is that it's going faster at the bottom. Next, we need to say that there's a net force inwards. How do you know this? Well, it's going in a circle. Since it's going in a circle, there must be a net force inward. So this is true at both points. And this is again where it's important to think about that RTZ coordinate system. That if I think about my point here at the bottom, my R direction is towards the top. My t direction is that way. If I think about this point instead, my r direction is down, and my t direction is that way, because it is rotating and following my point. Why is this a big oval circle? I think it's just to show that these two forces are both acting on it. So net force is inward in both cases. So that means down if you're at the top, up if you're at the bottom, inward to the circle. So now, here's the logic. The larger speed, right, we said it was faster on the bottom, has a larger centripetal acceleration. Why? Because centripetal acceleration can be expressed as v squared over r. So, if you have a larger speed, you have a larger centripetal acceleration, which means you have a larger net force, right? Because net force is just the mass of your cart times your centripetal acceleration. And again, we don't have any people falling off out of this as it goes through the loop because safety. So we have a larger net force at the bottom. And again, here I'm trying to talk you through the reasoning, because if you just look at this picture, you might either go, yeah, okay, that's the answer, or you might not understand. So we've started with larger speed at the bottom, we know the direction of the net force, and based simply alone on the larger speed at the bottom, we've said that the net force must be bigger at the bottom. Now, look at the forces on our free body diagram. We have a normal force and we have a gravitational force. Now we have the normal and gravitational force at both the top and the bottom. The gravitational force is fixed. The gravitational force here is equal to m times g. So the only force that can possibly change is your normal force, right? So we're saying that F net equals your normal force, and I'll write it the book way, plus your gravitational force. So gravitational force is really fixed. That's constant. So if your net force is changing, your normal force must be changing. So that's what you see in this picture, and this is a really important takeaway, that at the bottom, you have a really big normal force. At the top, yeah, you have a normal force, but it's pretty small. And the reason that's okay is because you need a much bigger net force at the bottom. So this is technically not uniform circular motion. UCM means uniform circular motion, because the speeds are different at the top and the bottom. But the top and the bottom points are special because the speed is not actually immediately changing right at these 2 points. And again, it's a little tricky to really see the argument, but if you realize that your net force and your velocity vector are perpendicular, that looks like uniform circular motion. And up here again, your velocity vector and your net force are perpendicular. So the whole situation is in fact not uniform circular motion, but we can analyze these 2 points as if it is. They do have different speeds, and at any other point on the circle, we would actually start to have tangential components of the force. But we don't have any tangential components of the force at the top and the bottom. So again, the important takeaway is that your normal force is changing. It's bigger on the bottom because you need a larger net force because it's going faster. So what happens if your roller coaster tries to go through the loop and it is going too slow? Now, one thing you might say happens, again, we imagine the loop going something like that, is that maybe it goes up and then just rolls back down. Sure, that could be something that happens. But if it makes it far enough up, you would actually imagine it just falling off, right? And instead of a roller coaster that you might think is really gripping on, you could imagine just rolling a marble. If I try to roll a marble, it might make it all the way around, but it might roll up and then kind of plop off. So this is going to happen if it's going too slow. And this speed, again, relates to the forces and the fact that if you have a certain net force towards the center and you have a certain radius, that by definition you must have a specific speed. So what this looks like is if you're going too slow, you actually fall off the curve, right? This is our circular track, you fall off, and that point where you fall off is the normal force becoming 0. Because up until that point, you're in contact with the surface, and the normal force is actually pushing you a little bit towards the center because you have a circular path. After that point, well, you just have the force of gravity, and you are no longer in circular motion. So let's consider another case then. What if you are going really fast, right? Again, the final argument we're going to make is that there's a special speed. We've said if you go too slow, you fall off. But what if you go too fast? This is actually okay. And the reason for that is that we know that there's some net force towards the center, and we've said that our net force is just going to be equal to our normal force plus our gravitational force. And in this specific case, when it's at the top, we can say that our net force in the r direction, which, right, r will be this way, is going to be the magnitude of the normal force plus the magnitude of the gravitational force, which is mg. But our net force has to also be the mass times our centripetal acceleration, and our centripetal acceleration is also equal to v squared over r. So a whole lot of things are fixed here. Mass is fixed, radius is fixed, mass is fixed, g is fixed. However, we are left with this velocity and this normal force. So if velocity increases, so can normal force. And what that corresponds to is your net force getting bigger. I just went off the screen, sorry. Because your normal force is getting bigger because your velocity vector is getting bigger. And it's a little weird to say because here, because it depends exactly on what the causality is. Causality is a tricky thing to tease out in this situation. But if it enters the loop, right? If it enters the loop and it has a really huge V initial, then at the top, you're still going to have a pretty big V. And so that's the idea, that the cause in this case is just the question of how big is the velocity that it's going into the loop with. And the idea being that that big velocity that has to be turned is being turned by a larger normal force. That larger normal force means you have a larger net force towards the center, so that's okay. So the takeaway here is you can go faster into your loop, and the normal force is going to account for that being bigger to give you a greater net force towards the center. So the last thing here is then the critical speed. The critical speed is the slowest you can go and still complete the loop. Go any slower, you fall off. Go any faster, you're okay. And the critical speed is when your normal force equals 0 at the top point. So here, your gravitational force is equal to your net force down. So this is F net. So again, you can have a normal force as well, but in this case, you now have that mg is equal to your net force in the r direction, which is equal to your mv squared over r. So we cancel our m's, and we get gr equals v squared, and so you're left with your critical speed to make it through the loop is square root of g times r. So your critical speed is going to depend on the radius of the loop. It is not going to depend on the mass of the car. And you can go faster than this and make it just fine because the normal force helps make your net force at the top bigger. But if you go any slower, you don't have enough of a net force to keep it going in a circle. So I encourage you to potentially think through this on your own, to maybe rewatch this section a second time. This is tricky to think through. I think this is one of the hardest things to think through in intro physics, but it's really testing that idea of using Newton's laws, using free body diagrams and the ideas of net force, and not just trusting your intuition, which unfortunately is sometimes wrong. To summarize all of these mind-bending things I've presented, first, centrifugal force is not a thing. Again, this one with the FU, it's a fictitious force, it's bad, it points towards the outside, it's not a thing. You shouldn't ever use it in my class other than to say it's not a thing. Objects rotating on the surface of the Earth actually need a small inward net force, and that force actually would change the apparent weight of the object at the equator, but doesn't appear at the North Pole. Whenever we're talking about a vertical circle, you actually need to have a minimal speed for that to be complete at the top, and we talked about that in detail with the roller coaster. And that minimum speed occurs when gravity is equal to the inward force at the top. I left that out. So at the top. And usually there's a second force that would be present otherwise, like normal or tension, but you find the critical by setting that equal to 0. So I hope that this has helped. Again, these are meant to be applications to help you think through circular motion and apply Newton's laws.